In this video, I'm going to demonstrate how to use linear functions to transform graphs. We know that the graph of a parabola, y equals x squared, has a certain shape. We even know some of the points that it goes through. For example, we know that it goes through the point 0, 0, that's its vertex. And another common point that we might know is it passes through the point 1, 1. Of course, there are others we could use, but those are two of the most common points. So suppose that I had the graph of another parabola, and I was given some information about that its vertex went through the point 1, 4, and it had another point that went through the point 3, 7. I'm interested in finding the graph, or the equation of this graph, and I'm going to use the transformation of the y equals x squared graph to find this. The way that we'll do the transformation is we are going to think of an association between the points of the y equals x squared graph and the points of our parabola we want to find. So here I've got a vertex, and I'm going to call that vertex, I'll call it point A, so that for my original graph I have 0, 0, and for my transform graph I have 1, 4. Similarly, I have a second point, which is, I lost that. I've got my point 1, 1, and that's associated on my new graph with the point 3, 7. So I get to associate those 2 points, and I'll call that commonly the point B. The way that we do a transformation is we think about our transform data. We want to take an input of t and use it to find z. And the way that we'll do a transformation is through this common strategy of we're going to go from a t coordinate to an x coordinate to the y coordinate and then back to the z coordinate. So we're going to go from our transform graph to our original graph, and then from our original graph back to our transform graph. We start by creating a table. So here we go. We're going to think of our t goes to x, and we're going to think of our y goes back to z. So notice that it's in reverse order. I've got my new data, my original graph, and then from my original graph back to my data. So I've got my point A, my vertex, and my second point. And let's take a look. When I have my vertex, point A, I start with a t of 1 and I go to an x of 0. So I go from a t of 1 to an x of 0, and then I go from a y of 0 back to a y of, or new data, z of 4. So I go from 0 to 4. For my second point, my t value is 3, and my z value is 7. My xy point goes from 1 and 1. Alright, what we do for transformations is we're going to think of finding a line that allows me to go from t to x, and I'm going to find another line that allows me to go from y to z. And the common thing when I'm finding the equation of a line, I need a point and a slope. So we have a point and a slope. And when I calculate the slope, my slope is always going to be the change in the output over the change in the input. For the line t goes to x, my output is x and my input is t. So I'm going to take the change in my output, 1 minus 0, and divide it by the change in my input, 3 minus 1, which gives me a slope of 1/2. And I have a point. I'm going to choose this point 1, 0. So I've got a point. My data are t and x, input, output. And I'm going to use the 1, 0 coming from my association of points A. So what do I have? My equation, output equals slope, input variable minus value, plus output value. That's the point slope form. And I'm going to find it to be most convenient to think of multiply by 1/2 as dividing by 2. So that's my first linear formula. For my second data, my output is z, my input is y. So it's my change in z over the change in y. And let's see what we have. My z changes 7 minus 4. And my y changes 1 minus 0. So the slope of this second line will be 3. Again, I need a point. This time my coordinates are input y, output z. Let's take a look. I could pick either one, but I'm going to pick 0, 4. So I've got a slope of 3 and a point 0, 4. My output variable equals the slope times my input variable minus the value plus excuse me, plus the output value. So I can simplify this as z equals 3y plus 4. And that will be the equation for my second linear formula. Alright, I need to get some space, so I'm going to clear this out and summarize what we've done. Let's review what we've done. We started with a graph, y equals x squared, the parabola. We were able to find a relationship that went from t to x, and it's this line, x equals t minus 1 over 2. We found a map that said from our y coordinates to our z coordinates, we found that to be z equals 3y plus 4. This creates for us a chain of relationships. We have a relationship that says how to go from t to x, from x to y, and from y to z. We can find an equation for z as a function of y by using substitution or composition. We'll start with the z equals 3y plus 4 equation, and we replace the y by its formula, x squared. So z equals 3 x squared plus 4. We now have z as a function of x. Next, we're going to take x and we're going to substitute its formula, t minus 1 over 2. So this is composition again. We're going to make the substitution, and so z equals 3. The composition, x gets replaced by t minus 1 over 2. That will be squared plus 4. And this is the equation of my new parabola. So notice what we did. The t minus 1 over 2 describes how my x coordinates, my inputs, going from t to x. I had to subtract 1 from t and then divide by 2 to get x. And then I'll square the result. That gives me y. And then I multiply by 3 and add 4. So that gives me my vertical stretch and shifting it up 4. That gives me the equation of my graph. And that's how all transformations work. If I can think about my original graph that I know, and then I can take my data's input coordinate, find a linear formula to go to x, and again find a linear formula that goes from the y to my data z, my output variable. Then I just do a composition and I've got my graph. That's how all transformations work.